Thank you, and a pleasure to be here at Dukinfield. Yes, two short talks here, so maybe about no more than 3 or 4 hours each, so you'll be released fairly soon. A couple of half-hour talks and maybe a short gap to ask any questions on the first one before we move on to the second. Roughly speaking, the first talk is about what the professionals do, and the second talk is about how you might get involved if you're interested as an amateur and you're interested in buying a telescope and doing some astronomy for yourself. Okay, so the first one, keeping an eye on the universe. So, telescopes have been around since the days of Galileo. He didn't necessarily invent the telescope, but he was one of the first to use a telescope and point it at the skies. And that was 400 or so years ago. And ever since then, telescopes have been getting larger and larger and larger, by which I mean the diameter of either the lens or the mirror that's used to catch the light has been getting larger and larger. So through this century, for instance, telescopes have been growing from the size of Galileo's telescope, where the lens might be a few centimeters in diameter to catch the light. Now, in the last century, we've been talking about telescopes in which the mirrors that are used to catch the light have been growing to sizes of meters. The one on the right there has a diameter of 5 meters. You can imagine what sort of size mirror that is. That on the right-hand side, the so-called Hale telescope in California, that was the largest telescope in the world when I was born. And it was the largest telescope in the world when I was a child, and it was the largest telescope in the world for a lot of my adult life. It's now been overtaken by others, which we'll see shortly. And I'm sure you're aware of the fact that as well as having various telescopes here on Earth, we also have telescopes in the sky, in other words, space telescopes, such as the Hubble Space Telescope, which has been around for some 35 years now. It's now a real old lady, but still producing some wonderful work. And more recently, the James Webb Space Telescope, which was launched on Christmas Day 2021, and is now up there in space looking out into the universe. So as well as having some fairly large telescopes on Earth and some modest-sized telescopes in space, there are plans to build some really big telescopes here on Earth. In the next few years, it's going to be a very exciting time for astronomers and astrophysicists, because telescopes like this are going to be coming online. And you probably can't make it out, but those two tiny dots at the front there are people. So you can see that this telescope is absolutely enormous. The mirror is some 40 meters in diameter. And the more light you can catch, basically, the more you can see. So there's been a growing trend from small to large. And it's difficult to see just how much that has changed over the years. So one way of trying to encapsulate that is to show the effective footprint of these mirrors. Not think about the whole of the telescope, but just think of how big are the mirrors. And this is a graphic which gives you an idea of just how mirrors have grown in size. This doesn't go back all the way to Galileo. Even the smallest mirror on this scale is actually 1 meter in diameter. The smallest lens or the smallest mirror, 1 meter. So that tiny blue dot in the top left is 1 meter. So all of these are to scale in size. And if you're having trouble encapsulating all of that, in the bottom left, the green poking out from the bottom, that's a tennis court to scale. And the bottom right, the orange, that's a basketball court to scale. And again, you possibly can't even make it out, but there is actually a human to scale there in the bottom right hand. So you can see mirrors have been getting ever larger from the beginning of the previous century in 1900 or thereabouts, getting larger and larger and larger. The largest telescope in the world at the moment is that one shown in yellow at the top, Gran Telescopio Canarias. Its mirror diameter is about 10 meters. I say about because it's not a large circle, because it's actually, as you can see there, made up of hexagonal segments. It's just easier to make that way. Rather than build one enormous mirror, it's simply easier to build lots of small hexagonal mirrors and then put them together to make a bigger mirror. So that's the world's largest at the moment. You can see on the right-hand side, there are definitely bigger ones coming along before too long. Down in the bottom left, to scale, we see space telescopes. And not surprisingly, although we would like to have really big telescopes in space, it's actually difficult to get a telescope into space. You've got to put it on the top of a rocket and send it off. So the actual size of the Hubble Space Telescope and James Webb Space Telescope mirrors are relatively modest by comparison with some of these monster telescopes that are going to be coming online before too long. So yes, the Hubble has been around for about 35 years and has produced some wonderful images. One of the things it's done is point at a relatively blank patch of sky where they thought, well, there's nothing much going on there. Let's just take a really long exposure and just see what we can see if we look nowhere in particular. And what they found is thousands upon thousands of galaxies. So basically, none of these dots or smudges are individual stars, with perhaps one or two exceptions, like there's a star there, but every other dot in this picture is a remote galaxy, much like our own galaxy. So the Hubble Space Telescope has been looking out into the universe and has told us that the universe is vast. Our own galaxy might contain hundreds of billions of stars, much like our own sun. But there are also hundreds of billions of galaxies out there, a little bit similar to the Milky Way. So that gives us an idea of just how tiny we are being part of our galaxy when there are so many other galaxies in the universe. So the Hubble Space Telescope, if nothing else, has given us an idea of scale. One thing you have to remember about the Hubble and indeed the James Webb Space Telescope is they can produce wonderfully detailed images of distant objects, but they actually cover a tiny part of the sky. So here's a chunk of sky. Where's the moon? The moon, remember, you can easily cover with your thumb. In fact, you can probably cover it with your little fingernail if you hold it at arm's length. So the moon is actually a tiny fraction of the whole sky, but the field of view of the Hubble Space Telescope is not this big square in the background. No, it's that tiny rectangle. The Hubble Space Telescope or the James Webb Space Telescope are designed to show a lot of detail of relatively distant or small objects. So the field of view is tiny. If you wanted to cover the whole sky by taking images with the Hubble Space Telescope, you would take hundreds of years to do that. That's not what it's designed for. It's designed to look in detail at objects. So we have images like this in which we see thousands of galaxies, even though that's a tiny patch of sky. And that allows us to work out how many galaxies there are probably in the entire observable universe by saying, well, we see that many in a tiny patch of sky. We don't think that that is in any way not representative of the whole sky, so we can deduce how many galaxies are actually out there. If we wish, we can ask the Hubble Space Telescope to look in detail at one or two or three galaxies, and it produces exquisite detail like this one of a beautiful spiral with two spiral arms and a large bar through the center of the galaxy. And by looking at hundreds, if not thousands of galaxies like this, we get an idea of how galaxies came to be, how they evolve, how they change, and why, for instance, our Milky Way galaxy looks the way it does. We've noticed in the last few decades that lots of galaxies, although the galaxies appear to be quite remote from each other, there are plenty of examples in which the galaxies are interacting with some of their neighbors. In other words, galaxies colliding with each other might sound catastrophic, but in fact, this happens more often than you might think. Our Milky Way might have collided with other galaxies in the past. Our Milky Way will be colliding with other galaxies in the future. And it is quite common to find galaxies that interact with each other. This galaxy at the top has got spiral arms which appear to be rather distorted because of the presence of this galaxy at the bottom, and vice versa. They tug on each other, much like the moon raises tides on the Earth. Galaxies raise tides on each other and can distort the shapes. And we can learn something about how galaxies behave by looking at lots of images like this. We can't watch them collide because the whole dance is too slow. It might take hundreds of millions of years for these two galaxies to collide with each other, so we can't sit and watch them. We don't have the patience to do that, but we can take lots of snapshots like this. And this again is an example of two galaxies that have already collided, and all the pink here indicates there's lots of new star formation as these galaxies collide with each other. Looking within our own galaxy, the Milky Way, we can see signs of stars being born, and we can see signs of stars dying. So this is pretty much what our sun will look like many, many years into the future, perhaps a few billion years into the future. Our sun will use up all of its fuel, which is keeping it hot and keeping the Earth warm at the moment. Eventually that fuel will be used up, and the star will slough off its outer atmosphere and produce a nebula like this. So this gas that you can see here, the pink and the yellow and the blue, are the outer part of a star that's been blown away to produce this nebula. And what's left is that tiny little dot in the middle. That's the core of the star that eventually produced this nebula. Our sun will eventually go through a phase like this. We figured that out by looking at lots of different stars and figuring out what is likely to happen to our sun. Some stars explode when they come to the end of their lives. Our sun probably won't. It'll just die like the previous image would show. Some stars blow themselves to pieces in what's called a supernova. And this is the remnants of a star that's been blasted to pieces, and there's almost nothing left of it. 99% of the star has been effectively blasted away and goes back into the gaps between the stars, and ultimately produces all the elements that can make new stars. It's a whole cyclic process. The Milky Way, if you like, is an exemplar for how you can recycle material. So it's been imaged by the Hubble Space Telescope, and perhaps you recognize this, a very famous image produced by the Hubble Space Telescope in its early days, the so-called pillars of creation, because rather than looking at star death, as we've seen in the last two slides, this is effectively what a stellar nursery looks like. Stars are born in nebulae like this. A nebula, a large cloud of gas, usually made of hydrogen, helium, maybe some other elements as well. And within these pillars that are being sculpted by new stars that are radiating energy out, within these pillars, these gas pillars, new stars are being born. So again, we can get an indication of how our sun came to be and how our solar system came to be by looking at other star systems out there. More recently than the Hubble Space Telescope, the James Webb Space Telescope, a somewhat different design. Again, perhaps you can see that it's got a hexagonal segment mirror because it's a larger system rather than the Hubble Space Telescope, which has got a mirror about the size of a person, a diameter of about 2.5 meters. The James Webb Space Telescope is somewhat larger and made of these hexagonal segments. That made it easier to manufacture because it was made on Earth, and then in order to get it on the top of a rocket, it was folded up like a piece of origami. The mirror was folded, and then it was placed on top of a rocket and then launched on Christmas Day 2021. And then once it was in space, it effectively unfolded, and they hope that the origami works and it unfolds back into its original configuration. Let's not get too technical, but actually the James Webb Space Telescope isn't in orbit around the Earth. It's sitting close to a dot in space, which is effectively a parking place. It's a bit odd to think that you can actually send something into space and actually take it to a particular location in space in which if you leave it there, it will stay there. You tend to think of, well, surely everything is moving relative to everything else, and the moon is going around the Earth and the Earth's going around the sun. But relative to the Earth, there are certain places in space in which you can park spacecraft. And that's where the James Webb Space Telescope has been sent. It's about 1 million miles away from Earth, much further away from Earth than, for instance, the Hubble Space Telescope, which is in orbit around the Earth. Again, let's not get bogged down too much in the technicalities, but one of the things that the James Webb Space Telescope is designed to do, apart from looking at how stars are born and how planets are born, it's also trying to look at the most distant galaxies possible, because we're interested not simply in knowing what's out there. If you look at very distant objects, because the speed of light is finite and it takes time for the light to reach us, if you look at the most distant objects, you're also looking back in time because it's taken billions of years for the light to reach us. So we are sitting here, the universe, to the best of our understanding, was born about 13.8 billion years ago. And so this is a timeline from when the universe was created all the way to the present day. So there's now on the right-hand side. So what various telescopes are trying to do is to look at the most distant objects, to look far back in time. Well, we'll never get to zero, but we're interested, when were the first stars in the universe made? When were the galaxies first put together? We think it was during a window somewhere in the first billion years or so. But one of the reasons the James Webb Space Telescope was built is to try and find out when. When were the first stars actually put together? Now, if we expand that out, we can see there's a few 100 million years after the universe was created. The Hubble Space Telescope can get back to about that point. It can look at distant objects and get back to about 500 million years after the Big Bang. The James Webb Space Telescope, larger mirror and a different set of instruments, hopefully we'll be able to get back further, and we'll be able to look back even further in time. And the question is, at what point do we find that looks like one of the first set of stars, the first galaxies? So far, even though we've been pushing further and further back along this line, the surprising thing is that even when we look at the very early universe, we still find stars and galaxies are there. So they must have been made much more quickly than we first thought. Before we had these telescopes, we thought maybe it takes a long time to make a star, to make a galaxy, and then we end up in the Milky Way that we see today. But it seems that the universe makes stars and galaxies a lot more quickly than we first thought. And that's one of the reasons we send telescopes into space or build telescopes on Earth, is to try and get a better handle on how did the universe end up the way it is, and how quickly does it take to make a star, make a galaxy, and can we understand the evolution of stars and galaxies since then to the universe that we see today. So this, again, is an image of the pillars of creation, dust clouds in which stars are being born, but this time it's imaged by the James Webb Space Telescope rather than the Hubble Space Telescope. So the structure very roughly looks the same, but the James Webb is able to see detail within these gas structures, these pillars, and is able to look at stars that are being born that would otherwise be rather difficult to see with the Hubble Space Telescope. The reason for a difference is not just the size of the mirror, it's because the Hubble Space Telescope is looking in visible light, whereas the James Webb Space Telescope is looking in infrared light. And I'm not going to go into the details, but I'm happy to take questions on that later if you're interested. James Webb Space Telescope is also able to see planets in the process of formation. So here it's looking in detail at a star. The star itself has been blocked out because, generally speaking, stars are very bright and planets are much less bright. So it's very difficult to see a planet going around a star if the star is really bright. It's like trying to see a tiny firefly if it's flying very close to a searchlight. You really can't see the faint one if you've got a very bright light in your eyes. So by effectively blocking out the light from the star, they can then see the light from any planets that might be going around. And in this particular case, this star, it looks like it's in the early stages of planet formation. We have this dusty environment in which we think this is all of the various small particles that will be collecting together to make planets. So in a sense, we're looking at how our solar system might have formed a long time ago. This is common with a lot of these images of very distant objects, is even though these are rather different to our own sun and own solar system, we can learn from these to get an idea of how we came to be here on Earth in our solar system by looking at other solar systems around other stars. The James Webb can look out into the universe and it sees not just one or two galaxies like the Hubble, it sees thousands of galaxies, sometimes spread across the universe, sometimes clustered together, as in this particular cluster. thousands of individual galaxies. There's looks like one star there. Virtually all of these other smudges are individual galaxies. And again, we're trying to understand galaxy formation and galaxy evolution. We can return to objects like the supernova that we saw earlier. And if we compare the James Webb picture taken fairly recently with the Hubble picture, the Hubble picture taken about 20 or so years ago, because this is a star that's exploded, if you look at it in 2005 and you look at it in 2025, because this object exploded something like 1,000 years ago, in a 20-year interval, it's got ever so slightly bigger. So if we compare, if I flick backwards and forwards between the two, if you pick one object like this little object there, perhaps you can see that as I flick backwards and forwards, there's actually evidence that the James Webb image is just a little bit bigger than the original Hubble image from 20 years ago. And that's consistent with the fact that this star exploded about 1,000 years ago. And so we can actually see changes. It's difficult to see changes continuously, but if we take images separated by years or separated by decades, we can see things in the universe changing. The James Webb has looked back in time and found evidence for huge black holes, regions of space from which light can't escape. It appears that black holes were made an awful long time ago. If we think of our original scale, we're looking back to the very early universe, and there is evidence that black holes existed very, very early on. Again, until we built telescopes, we didn't know whether black holes are a relatively recent thing or whether they were there in the very early universe. One of the important observations that the James Webb Space Telescope is making is looking at supernovae. They don't look very spectacular just by circling them. That doesn't help much. These tiny little dots in the center of each circle, the James Webb is looking at supernovae, stars that have ended their lives, because we think they are standard candles. They give us a way of determining just how far away are the galaxies in which these supernovae went off, because we think every supernova goes off with a certain bang and produces a certain amount of light. So if we look at how much light we can see, that gives us an idea of the distance to these galaxies. James Webb is actually checking whether or not these supernovae are standard candles, whether they all go off with the same bang in the first place. In other words, are we genuinely getting a good way of gauging the distance to these very distant objects in the universe? One of the most distant objects that the James Webb Space Telescope has found is a galaxy. Again, it doesn't look very impressive, perhaps. You wouldn't actually notice it unless there was a big white arrow next to it pointing at it. But what we've actually done is to say, well, we're interested in going back to the earliest part of the universe possible. The Hubble got us back to there. Well, according to the latest images from the James Webb Space Telescope, we've now got back to about that point. In other words, we're never going to get back to zero, but we've now got back to some 300 million years after the Big Bang, and there are stars, and there are black holes, and there are galaxies, even that quickly. So once the universe was born, it did not take long to make black holes and make stars and make galaxies. And that is a little bit of a surprise, because a lot of people assumed that it'll take at least 1 billion years to make all the stuff that we see around us today. And yet it appears to have been there even earlier than we think. And maybe the James Webb will be able to push even earlier if it takes more observations of more distant objects. Time's getting on, so I better say something about the third telescope I wanted to mention. It's a survey telescope. It goes under the rather awkward name of the Large Synoptic Survey Telescope, and now they've renamed the survey that it's doing the Legacy Survey of Space and Time. It's a large telescope which will be coming online in the next couple of years or so. And the idea is, remember the Hubble Space Telescope could only see a tiny patch of sky? Well, this telescope is able to see a huge chunk of sky. So huge I couldn't get it all in the slide. It's just the bottom of it there. How do you make a telescope that's able to see a large chunk of sky rather than a tiny chunk of sky? Well, you start with a huge mirror. So here's a huge glass mirror before it was coated with metal to make it reflective. You can gauge the size from the number of people standing around it. And no, that's not the camera they're going to use for this particular telescope. Just to give you a sense of scale, the camera that's in your mobile phone, or probably in your mobile phone, is just a few millimeters or so in size. And relative to that, the size of the chip in, for instance, the Hubble Space Telescope is about 40 millimeters. So that's roughly the size of the chip in the camera in the Hubble Space Telescope, 40 millimeter on a side. But the camera that's going into this survey telescope, by comparison, is absolutely huge. If that's the size of the chip in the Hubble Space Telescope, imagine taking that chip and making it 9 times bigger, and then add another batch of those, and then another, and then a few more. So this chip is going to be, sorry, it is, because it's actually been made, this chip is approximately the size of a coffee table. It's literally about that size. And it doesn't contain a few million pixels, it contains a few billion pixels. 3 billion pixels. Every time it takes a picture, it generates an image with 3 billion pixels. And I can't possibly give you an indication of what that might look like because I haven't got enough pixels on my laptop or on your projector. So let's just imagine, let's take a tiny, tiny, tiny bit of what that will see. That, we hope, this is simulated because it doesn't take images just yet, we would expect to get thousands of stars and thousands of galaxies and probably hundreds of solar system objects caught. But that is only a tiny part of the whole image. The entire image would be 3,000 times larger than what you've just seen, and it will take an image like that every 15 seconds of the night sky, and it will literally try and survey everything that's out there. The Hubble Space Telescope, the James Webb, are pointed at things that we know are interesting. This survey telescope will basically survey the sky and try and find what objects are in our solar system or in our galaxy or beyond our galaxy. One of the questions we're trying to answer, for instance, is we know that as well as all of the stars and dust and gas that we can see, we know, for reasons I'm not going to go into details about, we know there is another type of matter out there called dark matter, which is very difficult to see, essentially impossible to see. But do we know whether this dark matter is uniformly spread throughout the universe, or do we think it's clumped? The answer is we don't know until we do proper surveys of what's out there. So, again, coming online in the next year or two, the wonderfully named European Extremely Large Telescope. You can see that their ability to name these things is somewhat limited. Again, notice a couple of people down the bottom there. There's also a couple of people standing on the gantry. A telescope with a mirror 40 meters in diameter. So remember, that was the largest telescope in the world at the top there, and on the right-hand side, the European Extremely Large Telescope. That's not necessarily the largest one we can ever conceive because, well, scientists and engineers are always thinking of, well, could we build one even bigger? Because that will collect more light and we'll see even more distance and hence back in time in the universe. We'll see even more detail of what's going on in star formation. The question is, could we ever build one the size of that red circle? 100 meters in diameter. Well, it's on the drawing board. No one's got any funding for it because it would be too expensive. But they have thought, well, if we did ever build a telescope 100 meters in diameter, well, what would we call it? We've already got telescopes called the Very Large Telescope. We've already got the European Extremely Large Telescope. So what on earth would we call something that's 100 meters in diameter? Some people have said we ought to call it the Owl. Is that because owls have big eyes? No, it's because that would be the Overwhelmingly Large Telescope. So there's always a drive to build different types of telescopes, and we need them all. We need survey telescopes to look at the entire sky and find out what's out there. And then when we've done that sort of survey, which will take years, then we can say to the James Webb Space Telescope or the Hubble Space Telescope, go look at this object and go look at that object and go look at that object. These are the interesting ones. Survey what's out there and then tell space telescopes or large aperture telescopes like the European Extremely Large Telescope, go tell them to look in detail with a very small field of view at some of these interesting objects. With all of these different types of telescopes working in concert, then hopefully we'll be able to answer some of the questions we still have about the universe. But perhaps more importantly, these telescopes will tell us the questions we haven't thought of asking yet. Thank you all very much.